Hi guys, today we're going to be looking at 2.1 and 2.2. All right, so here is the objectives for 2.1. So feel free to pause this and take a minute to see what we're going to be going over here. All right, let's look at relations. So what is a relation? It is any set of ordered pairs. So they could be a function, they don't have to be a function, it's just any set. So when you're looking at two key things, which in this case are domain and range, anything in the X position is going to be domain. Anything in the Y position is going to be your range. So let's go ahead and look at this first example. I need you to find the domain and the range of this relation. So domain is all of your X's. Remember, X's come first in an ordered pair. And then my range is going to be all of my Y's. And Y is always the second number in every point. So if I was writing what my domain is, it's going to be the point 0, 1, 2, and 3. And if I was writing the range, it's going to be 187, 212, 225, and 238. All right. One thing to note is if any numbers like double, you don't have to write them twice. So for instance, let's say in the domain, there were 2 3s in the X position. You would only have to write it once. All right, moving on. Let's look at the difference between a function and a relation. So a function is a special set of relations. So it's kind of like how not every rectangle is a square, but every square is a rectangle. So not every relation is a function, but every function is a relation. So it's more like a specialized kind of a relation. And it's got a correspondence from the first set or the domain to the second set called the range, such that each element in the domain corresponds to exactly one element in the range. So basically, you do not repeat your domain. If any values in your domain repeat, it is not a function. If any values in your domain do not repeat, then it is a function. The range does not matter. So you can have repeating numbers in the range, just not in the domain. So to illustrate this, what I tell people is about this little chart here, right? So we need to see if this is a functional relationship. So using boys and girls works quite nicely because we think that a functional relationship, between a boy and a girl is when they are committed to each other, right? So there's only one person going to um, their girlfriend. So Brad goes with Jamie. Brad and Jamie are in a functional relationship because there's only one line. Brad only has one girlfriend, Jamie. Same with Zach, right? But Aaron, if we see Aaron is attached to both Lisa and to Sarah. This is not a functional relationship. That relationship is not going to end well. So if we look at this, this could have been a chart of functional relationships, but because Aaron is not in a functional relationship, that means that this chart would not be a function. This is not a chart of functional relationships. All right, so let's look at this relation and see if it is something that is a function. All right, so what I have to check on is I have to make sure that all of my domain values do not repeat. So since all of those are different values, this would be a function because none of them repeat. Again, it does not matter that I had 2 5s in the range. That doesn't matter. It's only whatever your domain is. So since my domain values do not repeat, this is a function. So yes, it is a function. All right, so now I have to determine whether the equation defines y as a function of x. Okay, so remember, what we can't have is 2 x's that are the same. All right, so we can have 2 y's, but we can't have 2 x's. So what I'm going to do is I'm going to go ahead and solve this for y. And if it ends up with one answer, then I'm good. If it ends up with 2 x's that could be the answer, then I'm not good. So if I'm solving for y, first I'm going to subtract the x squared over. And then to get rid of the square, we saw that last week, we take the square root. And remember, when we take a square root, we have to have a plus and a minus. Okay, so I don't know what this is, but that's as far as I can get it. But this y equals the plus and the minus of this answer. So since that one y is attached to multiple x's, that's going to be not a function, because there is more than one x that can go to that y. All right, let's look at how you would know if it's a function or not a function based on a graph. All right, so sometimes you're going to be given a graph, and we have to determine whether it's a function or not a function. All right, so what we do is the vertical line test. If I can draw a vertical line down this graph at any point, and I do not hit 2 points on it, it's a function. So no matter where I drew that line, I did not hit the graph more than once. Like this one hit it here, this one hit here, this one hit here, all down, all those little lines that I drew, I'm only touching that graph in one spot. So yes, this one is a function. Let's look down at this one. Okay, so any point, I can choose any point to draw a vertical line down. But if I can find any point on this graph, if I drew a vertical line, I would hit this more than once, it would not be a function. This one's okay, it is a function. All right, let's look at this one. Now, here's the deal. While I can find a place right here where I only hit it once, I can find lots of places where I'm hitting this graph more than once. And so since I can find all these places where vertical lines are hitting more than once on this, this is not a function. So that does not pass a vertical line test. And let's check our last one. This one, I don't think there's any place I could pick to draw a line where I'm going to hit this more than once. So this one is a function. All right, moving on, let's look at function notation. Okay, so up until now, for the most part, we've seen things written like this. So y equals x squared minus 2x plus 7. Now I've got this weird thing here. It's an F with parentheses and an X in the middle. But what this is called is function notation. You say this as F of X. So it's saying it's a function of X. All right, so if it's a function of X, that just tells you that you're only going to see that notation when it is a function. So when you see that notation, you know it's a function. So you know this is going to be something that every X is unique. It's only going to spit out one Y value. You're not going to have doubles. Also, it's going to pass a vertical line test if you looked at a graph. Okay, so when you see that, it's just a fancy way of writing Y. So if you wanted to rewrite it like this, you could. But it also, I know I've told you in class before, mathematicians are lazy. So what this function notation does, see how there's an X value here? It lets them say, hey, will you calculate what my Y value equals or what my range equals if the X or the domain is this number? So in short, what this is saying is plug -5 into X and find the Y value. So they're just asking what is the answer if you plug -5 into your X's. So when you see that notation, it confuses people sometimes. They think, oh, I have to multiply everything by -5 because usually parentheses mean multiplication. That's not the case. This is called function notation, and that's the number you plug into the X. All right, so I would write this as F of -5 equals, and now I just plug in the -5 into the spots where the X is. Everything else stays the same. And then I just calculate. So -5 squared is a positive 25. -2 times -5 is a positive 10. And now I just go ahead and add. 25 plus 10 is 35. 35 plus 7 is 42. So F of -5 equals 42. If you were to write that in a table, what it would look like is at the point -5, my Y is 42. All right, let's look at evaluating with a graph. Okay, so use the graph to find f of 5. Remember, this is an x value because function notation is f of x. So what was there was an x. So if it's there, that is an x value. All right, so f of 5. That means my x value is 5 right here. And it's saying, what is the y at that point? So on a graph, I would just move up. I'd say, okay, well, that's where it's hitting. Let's see what the y value is at that point. It's 400. So f of 5 equals 400. All right, so now it says for what value of x is f of x equal to 100? So remember, this is the x value. This, remember, was our y value. So they're giving us our y value this time and we're working backwards. So I go to the y value of 100, which it looks like it would be, let's say about there is 100. So I would draw my line over. And it looks like I'm hitting right here. Well, what x value is that? It looks like 9. All right, so for what value of x, I would say f of 9 equals 100. Or you can say x equals 9. All right, let's look at graphing functions. In class, I'm going to have you actually graph this. But on the video, we've already gone over graphing, so I didn't want to waste your time. So I already have it here for us. But let's go ahead and read this and talk about it. So it says graph the functions f of x equals 2x and g of x equals 2x minus 3 in the same rectangular coordinate system. So how do we do that? Well, remember before we made our little tables, right? X and y, or f of x in this case, because now we have function notation. And they want us to start with -2 and end with +2. So that's where these numbers here come in. And we're just plugging it in, right? So I plug in -2 into this. So 2 times -2, that's where I get that -4. And you just continue along and you should get the same table of values, just like we've done the other week. All right, and then for g of x, right? So that just means, okay, I've got another function, but I already have f of x, so now I'm going to pick g to be my letter. But it means the same thing, still function notation. So same thing, I'm just going to make the table. If I plugged -2 in, that'd be -4 minus 3, and that's how I get that -7. You just continue that along, and you plot the points again like you've already been doing. In the next unit, we're going to be getting into transformation. So this is just looking at how these compare. So you can see the f of x of 2x is this red line, and g of x, 2x minus 3 is that blue line. So you can see that they're almost exactly the same. In fact, they're parallel, right? They are moving at the same rate. And it looks like g of x is just down 3 units. And so it's the same graph shifted down 3 units, which it's curious, it's got this -3. We're going to get into this more later, but just remembering how to graph and being able to compare them. All right, let's look at domain and range. All right, so remember, we already did domain and range from ordered pairs. So for instance, when I had 0, 1, 1, 2, and I'm just making numbers up. If I was doing the domain, it was all the x values. If I was doing the range, it was all the y values. But now I've got a graph, so I don't have the points to look at. So how do I do this? Well, for domain, you do this the way you read it, so left to right. What is the leftmost x value? Well, if I was drawing a nice little box here, the leftmost x value would be here, right? And so that's at -2 for my x value. Remember, I'm looking at my x-axis. The farthest that I go right would be this dot here. And what value is that? It looks like 1 on my x's. So if I was writing my domain, I would write it -2 to 1. And notice the parentheses and brackets. We talked about this last time with interval notation. I put a parentheses at -2 because that was an open dot. I put a bracket at 1 because that was a closed dot. So it included it. So this would be my domain. If you wrote it in inequality notation or set notation, it would be all x's such that it was between -2 and 1. All right, so what if I'm doing the range? I'm going to do the same thing, but I have to look at my y's now. So instead of looking side to side, I'm going to look at the very top and the very bottom of this. So just like I went left to right, so smallest to biggest, I do the same thing for range. So smallest to biggest. So what is the lowest most point on this graph? The lowest most point is this one. That is the farthest down on the graph that it goes. Well, what y value does that correspond to? It looks like -1. And it is an included dot. So my range goes from -1. And then what is the very topmost dot? It looks like this one right here is my topmost dot. What y value does that correspond to? A 2. All right. So, and that is an open dot, so it will get a parentheses. So notice that these are not the same numbers in the domain of range. That's okay. They do not have to be the same numbers. It's very left to very right, and then very bottom to very top. So those sometimes are the same and sometimes are not. If I was writing that in inequality form, it would be y such that y is sandwiched in between -1 and +2. All right, so let's look at a continuous graph. So this graph is a little bit different. It's not just little bits with endpoints. This extends forever here and extends forever here. All right, so if I'm doing domain and range from here, I still have to do the same thing. Now, this is where people's minds, you really have to focus on left to right when you're doing domain, and then bottom to top when you're doing range. So we're going to do domain first. If I'm doing domain, I have to focus on left to right. So I kind of take my pen and I'm like, okay, I'm going to go until I find a starting point. And it looks like right here, that was a starting point for me. So this is the first value. Well, what value is this? I'm going to go ahead and darken up my X and Y axis a little bit so we can see where they're at. They're there, but they're a little bit light. Okay, so what value is this? This looks like it is at -2. So that's at -2. So it goes from -2 and it is included because that was a solid dot underneath there. All right, so then is there a place that stops on the right? Well, no, because this arrow extends on forever. And even though this one's going up, it's also going right. It's not just going straight up, it's going to the right as well. And same here. While the arrow is going down, it's still going to the right. So it's still covering all these X values forever this way as it continues to go up and to the right and down and to the right. So my domain goes forever. There is no right stopping point. So it's from 2 to infinity. If you did that in this set notation, it would be X such that X is greater than or equal to 2. Because it's starting, oops, sorry, -2. I need to change that. So it's starting at -2, and then it extends forever in my domain. There is no place that it's stopping. All right, let's flip our mind now. We have to look at range. All right, so if I'm looking at the range, I'm going bottom to top. Okay, so I am looking somewhere on the bottom where it's going to stop. But I have this arrow that's going down, and it's going to keep going down, going down, going down, going down forever. So it will never stop because it has an arrow indicating it goes forever. So the very bottom number would be -infinity. And then if I look, okay, is there a cap? Is there a max value where it can't go any farther? Well, this is going up forever. So it, again, will never ever stop. It just goes up forever. So my range is -infinity to +infinity. And so you could write that as y such that y is in between -infinity and infinity. And actually, I shouldn't have the line under it because you cannot reach -infinity, infinity. Okay. Let's look at x and y intercepts. I'm going to do this one a little bit quicker because, again, this is something that we already covered. So if I'm looking at x-intercepts, those are going to be these ones highlighted in red, anywhere it's crossing the x-axis. So you could write this in a couple different ways. X-intercepts, you can write them as points. Sometimes they're written as points. So if I wrote them as points, this one would be -3, 0. This one would be -1, 0. And this one would be 2, 0. So I could write them like that. So -3, 0, -1, 0, and 2, 0, because those are the places that's crossing. Sometimes you also see it written as x equals -3, -1, 2. So depending on the format, those are your x-intercepts. All right, what about your y-intercepts? Well, that is going to be anywhere it crosses your y-axis. You can see that as that one with the blue dot. So as a point, that is 0, -6. So y-intercepts would be 0, -6, or y equals -6. All right, let's move on to 2.2, more functions in the graphs. Feel free to pause this. And let's go ahead and talk about these graphs. So these are increasing, decreasing, and constant intervals. All right, so this confuses people sometimes because they're not sure how to look at graphs to know whether it looks like it's increasing or decreasing. So you do it from left to right, just like you're reading anything. You always look left to right. And if it looks like you would be climbing a hill from left to right, that is increasing, just like you'd be increasing in altitude if you're climbing that hill. If it looks like you'd be falling down or sliding down a slide, sliding down a hill, then you would be decreasing. And if it looks like as you're walking left to right, you're not going up, you're not going down, you're just staying straight, flat, horizontal, then that is a constant interval. So like this one, if there was a little person here and he went up here, you could see that he would be increasing in altitude. He would be climbing up a hill. So that's an increasing interval. This one, this person could sit down and slide down the slide. So that is a decreasing interval. You're decreasing in altitude. And the constant, this person, as they walked, would not be getting higher, would not be getting lower. They're just staying on that flat surface. That is a constant interval. So let's go ahead and look at writing them. One thing I don't like about this first picture, this is a cubic function, so it should have arrows going left and right. Okay, so if I was looking, I might have multiple increasing and decreasing intervals on each picture, which is the case here. So if you look, this portion from negative infinity, right, because it goes down forever. So from negative infinity all the way up till you reach the top of this peak where it looks like that's at -1, that is an increasing interval. So if I were writing increasing intervals, I would have to say, okay, from negative infinity, because again, it's going down forever, all the way till I reach that point where I'm at -1, which by the way, you always use x values for reference, to -1, I am increasing. But then if you look at it, what happens at that point? From the top of that hill, it looks like now I'd be sliding down till I hit that portion. So this doesn't just have an increasing interval, this also has a decreasing interval. So I would, okay, I need to add one for decreasing. And it is decreasing all the way from that -1 until I hit at 1. Okay, well, what happens after that? Well, let's look. So starting at 1, what's happening? It looks like I am increasing, and that arrow tells me I'm increasing forever. So then I've got a second increasing interval. So I use my U, my union, right? And that goes from 1 to infinity. A lot of people ask, why do you not use brackets here? Because those are included numbers. They are, but since um, this -1 is in both the increasing and the decreasing, I don't include it in either. I leave it in parentheses. Basically, for increasing and decreasing, I always have parentheses. I never use brackets. Some mathematicians use brackets. I personally don't like them. All right, let's look at our next picture. If I'm doing increasing and decreasing, let's look at the first thing that we see. Again, this one really should, oh, it does have arrows. Yay, it's got those arrows there. Okay. So, oops, sorry, guys. So if I am looking at this from negative infinity, right? I'm going negative infinity. It looks like I'm increasing all the way till I reach the top of this peak. So let's figure out what that is. Let me again make my X and Y axis a little bit darker so we can see a little better. Okay. So what is that value? It looks like that value is right here. That looks like -1. Okay, so I have an increasing interval from negative infinity all the way till I reach -1. Let's see what happens after that. At -1, then I start falling, 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 falling. The arrow tells me I am going down forever, and that's going to keep going to the right forever. So for all the rest of my x values, from -1 all the way to positive infinity, it looks like I would be decreasing. So decreasing would be from that point at -1 all the way to infinity. All right, let's look at relative mins and maxes. All right, so sometimes, just like what we saw in that last cubic function and what you've got going on here, this is going to go up forever and this is going to go down forever. So if anyone said, hey, what's the maximum value or what's the minimum value? You'd have to say, well, there isn't one because it goes up forever, so there's no max. It goes down forever, so there's no minimum. However, it does have these little bumps, right? It's got these little bumps here. And so it might have what's called a relative minimum or a relative maximum. That just means, hey, I do have kind of this minimum value here before it turns and goes up again. However, it's not an actual minimum because it goes down forever. It's a relative minimum. Same with this one here. This is a relative maximum because it is the highest point relatively, but it will never be the highest point because it goes up forever on the left side. And instead of relative, sometimes they use the word local. So if it asks for local, it's the same thing. Local, relative. All right, so let's go ahead and look at these graphs. Again, I don't really like this graph on the left because it does not have the arrows indicating, but we know this is a cubic function. It goes on forever. It doesn't have the little dots saying those are segments. So it is increasing and decreasing forever. Does it have any relative mins and maxes? Well, yes, it does. So let's look at maxes. It looks like right here at that point -1, it has a relative max. And does it have a relative minimum? Yes, it does, right here. So this is a relative minimum. Now we have been dealing with X values for all these. So if I was doing this though, you can't, since it's a max and a min, those are more Y things. So you would have to actually put what they are. So this relative max occurs at, looks like -1. I'm going to guess it's about at 3. And the relative minimum occurs at the point 1. Let's go -2. And so you can either use a point or you can actually use the height or the Y value. All right, so let's look at this one. Is there any relative mins and maxes? Yeah, there is. Let's look at maxes. This would be a relative max. And this would be a relative max. Because right before them, after this, it goes down. After that one, it goes down. So those are maximum values before the graph makes a turn and goes down. So this point, that would be a relative max. And so I could say at -1, because that is its height, it's hitting at -1. And I could say that this one is a relative max as well. And that's at 1, 2, 3, 4, 5, 6. So a relative max at 6. And then let's see if there's any relative minimums. Well, there's this one. And there is this one. So then this one would be a relative minimum. And that would be at -1, 2, 3, 4, 5. So at -5. And this will be relative minimum at 1. At 1. And that actually, this relative minimum at -5 would be an absolute minimum too, because it is the lowest point in the graph. And same with its relative max at 6. It is a relative max, but it's also the absolute max because it's the highest that graph goes. All right, let's talk about symmetry. So we can figure out whether an equation is going to be symmetric on the y-axis, symmetric on the x-axis, or symmetric on the origin. And so to do this, we plug in negative values and see if we get an equivalent equation. So what's a little bit different and something you have to get used to, it seems a little backwards, is if it is symmetric to the y-axis. Let's look at what a picture of this would look like. If it was symmetric to the y-axis, that means that it might look something like this, right? It could fold over and fold perfectly over the y-axis, which is right here, right? So it would fold perfectly over the y-axis. So to test for that, a lot of people are like, oh, well, it's the y-axis, so I plug in a negative for the y, but it's not. You plug in a negative for the x. So, and if it helps a little bit, this would have to match this, right? So what's the difference? The y isn't different, but look, that would be the positive x value, that would be the negative x value. So that's why you would plug in the x's to see, does it have that symmetry? So same height for y, different sides of the y-axis for the x. So then same thing when you're looking at symmetric to the x-axis, instead of plugging in negative x, it's negative y. So let's just sketch a graph. Look at that real quick. So if I was sketching a graph that's symmetric to the x, it might look something like this. Forgive my drawing a little bit. So if it was symmetric to the x, you should be able to draw one straight down the middle, and it would be a mirror image across the x-axis. And so what you're looking at, let's say these two dots, so same x value, right? I'm hitting on the same x, but I've got the positive value of the y, the negative value for the y. All right, and then symmetric across the origin, that one, you have to do both. So if it's symmetric across the origin, then that means that negative x for x and negative y for y should give you the same value of the equation. All right, so let's see what that actually looks like in action. So we are going to determine if each of these equations are symmetric along the x-axis, the y-axis, and the origin. So let's go ahead, let's do the x-axis. So for the x-axis, what I do is I plug in negative y for y and see if it ends up as the same expression. Okay, so if I do that, instead of that positive y, it's going to be negative y. Everything else stays the same. And then I solve for y. So this is almost done, except that's negative. So that means that I have to divide by -1 to get rid of it. So that is negative x squared plus 1. Well, that is not the same thing. So an equivalent equation would mean I would end up with this exact expression when I do the math. That is not what I got, right? That is not the same. It looks similar, but the x squared is negative and the 1 is now positive. So no, it is not equivalent along the x-axis. All right, well, let's try the y-axis now. So to do that, I plug in a negative x for any x, and I solve it and see if I end up at the same place I started. So if I do that, I'm just plugging in a negative x anywhere there's an x, everything else stays the same. So now I solve. Well, what is anything squared? Well, anything squared is positive, right? So a negative times a negative is a positive, positive times positive is a positive. So this is what I end up getting because I know it's going to be whatever the x is squared and it will be positive. So in this case, this is the exact same expression I ended up with. So yes, it is equivalent along the y-axis, or sorry, symmetric along the y-axis. Okay, so let's try the last thing, which is going to be the origin. And for that one, I plug in negative x for x and negative y for y and see if I end up with the same thing. Okay. So I went ahead and just knew that that square was going to be positive, but now I have to divide by negative 1. Nope, not the same thing. It is not equivalent across the origin. So in this case, it was only equivalent along the x-axis. Sorry, not x, y-axis. All right, so let's go ahead and try this one. So first I'm going to try, is it equivalent along the x-axis? So for that, again, I plug in negative y for y, and I see what happens. Everything else stays the same. And nope, that is not the same. This ends up being a negative 2y, and I need it to be a positive 2y. So no, it is not equivalent over the x-axis. Let's go ahead and now try the y-axis. So for that, I'm plugging negative x for x. And in this case, yes, I have the exact same thing I started out with. So again, we have one that is equivalent on the y-axis. All right, so let's go ahead and try for the origin. So that's going to be negative y for y and negative x for x. And again, nope, we do not end up with the same thing. So that one is a no as well. All right, even odd functions. So this is going to be very similar to what we are just doing. The process is going to feel familiar. So if it's an even number, it's not an even number. If it's an even function, that means that the right side of the equation, so the right side, so only the part with the x's, does not change if x is replaced with negative x. If it is an odd function, then every term on the right will change signs. So that's what this means right here, where it says when I plug in that negative x, if the whole thing, if everything on the on the right gets negated, flip signs, then that's an odd function. So if you do this and you plug negative x in and it doesn't stay the same, or if everything does not change, then it is neither. It's neither odd nor even. So let's go ahead and check it out. So let's determine if this is an odd or an even function or neither. All right, so again, I only do it on the right side, so this does not change. But what I do is I say, okay, I'm going to plug in a negative x anywhere that there is an x and see if I end up with an equivalent expression. Okay, that will mean it's even. If everything changes signs, it's odd. If it's a mixture, some things change and some things don't, then it's neither. Okay, so I've plugged in negative x. Let's see what happens. Negative x to the fifth power. Okay, so remember when you had a square and I said, okay, a negative x squared was always going to be positive because anytime you square, it's always a positive number because a negative times a negative is a positive. And same with two positives. Well, now when you have something to the fifth power, what you have to do is I use my hand and I say, okay, I do it 5 times. So negative x times negative x is a positive x squared. Okay. Positive x squared times negative x is a negative x cubed. Okay. Negative x cubed times negative x is a positive x to the fourth. Positive x to the fourth times negative x is negative x to the fifth. Basically, if it's an odd number and it starts out negative, it will stay negative. That's how you get the negatives. Okay, but there's nothing going on with the 1. So I look at this. Okay, when I plugged in the negative for all the x's, what happened? This one changed, right? So it went from a positive to a negative. Okay, so that means it could be an odd function if everything changed. So now let's check out the next thing. This 1, did it flip signs? No, it did not. So since it did not change, this is neither odd nor even. So that's a neither. All right, let's check out this next one. So again, I'm going to do this by substituting in a negative x and seeing what happens. So anywhere there's an x, I'm plugging in a negative and I'm going to check it. So what happened over here? So negative times negative is positive. Positive times negative is negative. And negative make a positive. So now I'm going to check what happened here. It looks like it changed. Okay, let's look at the next one. What happened here? It also changed signs. So since everything on the right changed signs, that means it is an odd function. If everything had stayed the same and not changed signs, that would have been even. All right, let's look at piecewise functions. All right, piecewise functions, those are just functions in which, depending on what the number in your domain or your x's are, you use different equations to solve. What do I mean? So let's look at this one, C of G. It has this value of 40, and so all those values are going to be 40 if the number you plug in is anywhere between 0 and 15. And it includes 15 because it's got that or equal to there. Okay, however, if your value that you plug in is bigger than 15, then you have to plug it into this equation. So it's kind of like, depending on what value I pick, that's how I know which one to use. So let's look at a couple of these. So this first one, it's a C of 5. C of 5. Okay. C of 5. 5 is going to fit in this range. 5 is between 0 and 15. So that is this. There's nothing to plug in. So that means if it's telling me it has to be 40, then C of 5 equals 40. My work is done. All right, let's move on over here and look at this one though. This is C of 50. 50 is in this range. It is a number bigger than 15. So to solve for this one, I have to plug it in. So C of 50 is going to equal 40 plus 0.60. 50 minus 15. Okay, let's go ahead and work this down. So that's going to be 40 plus 0.60 times 50 minus 15 is 35. Okay, at this point, I'm going to pull out my handy dandy calculator and I'm going to say 0.6 times 35. That gave me 21. Just using my order of operations. And I end up with C of 50 equals 61. All right, and let's see about graphing a piecewise. Okay, so when I do this, I'm going to graph this piecewise, and I'm going to go ahead and do -2, -1, 0, 1, 2. Let's go ahead and go up to 3. Okay, so this tells me that if I am less than or equal to -1, my answer is going to be 3. So anything that is less than or equal to -1, I can just say is 3. However, anything that is bigger than -1, I have to use this equation. So let's go ahead and do that. So this is bigger than -1. So I plug it into the equation. 0 minus 2 is -2. Okay, I'm going to go ahead. Everything else is bigger than -1, so I just keep plugging into the equation. 1 minus 2 is -1. 2 minus 2 is 0. And 3 minus 2 is 1. Okay, so now I'm just going to go ahead and plot this. So I have a dot at -2, 3, at -1, 3, at 0, -2, 1, -1, 2, 0, and 3, 1. So this looks weird. Here's the thing, with a piecewise, you connect the two parts that go together, right? So those went together because they are both from this first part of the equation. These then go together, and it looks like that would continue up. What do you think is going to happen on this left side? Well, if it's at 3, it's just going to continue this way. So that is what the graph looks like. However, I have just made a mistake. At -1, it is included with the 3, which means I would have to think about what would that look like at -1 here. It would probably be an open dot like that. And so that is what the piecewise function will look like graphed. I hope you've learned something today, guys, and I will see you next time.